It's 2:05, so let's go ahead and get started. Hopefully you had a nice little break. Thank you for joining us again for paper session number 6. This is on large language models at work. I think we should just jump right into it, but let me start with a couple of housekeeping notes. So I'm going to ask speakers to stick to 15 minutes for their talk. That should give us about 15 minutes at the end for any questions. Attendees, please use the Q&A feature for asking questions, and it would help if you can indicate who your question is for in your question. That'll help us at the end to direct your questions. So without further ado, Leland, you've got your slides shared already, so thank you. Why don't you go ahead and start?
Great. Okay, yeah, thank you all. Thank you for including us in the program. I'll be talking today about total recall, evaluating the macroeconomic knowledge of large language models. And this is work with Akil Kara and Paul Soto. Akil's at Carnegie Mellon University, is our intern at the board. And the usual disclaimer applies. Opinions expressed herein are those of the authors alone and do not necessarily reflect the views of the Federal Reserve System. So there. Okay, so let me talk about the motivation first. We're economists, and we see two ways that economists would like to use LLMs, among others. One is to help with historical analyses, kind of as a brainstorming partner, suggesting hypotheses, discussing possible mechanisms, the kind of early stage research and brainstorming that we do sometimes. So you could think about asking about the recession in the 1990s. Was it unanticipated? When did folks really think that a downturn was likely? That's the kind of thing that you might want to discuss with an LLM while you're thinking about possible research ideas. Another prominent use is using LLMs for forecasting. And a lot of papers have done this at this point. The idea being that you can ask the LLM to forecast, say, the next 4 quarters of GDP or some other variable. Maybe you feed it additional data, say, here's some historical data. What's your best guess for where things are going? If you're doing that, then you often have to do some validation, and a lot of that validation is going to end up being in sample before the knowledge cutoff, because the knowledge cutoff is usually very recent. So we're going to try to say something about both of those uses. For the first use case, we're just going to be documenting and testing the recall of important macro data series. The idea being that if LLMs will need to know history if they're going to make good analyses or be a good brainstorming partner. And we're honestly just curious about how good their recall was. How much economic knowledge do they have historically? On the second topic, for forecasting, we try to develop some tests for look-ahead bias, which we think is a pretty important topic here. So the idea is we tell the LLM to act as a real-time forecaster living at a certain date, tell them that they shouldn't use post-date T information when making their estimates. And then we're going to be checking if the recall errors are correlated with surprises from after date T or data revisions from after date T. And what we're getting at here is that if the LLM can't act as a real-time forecaster, can't really pretend to be a real-time forecaster, then there's going to be problems when we try to use pre-knowledge cutoff data to do back testing. So hopefully that'll be clear as we move on. So our basic setup is, here's an example of a truncated query. So one of the queries we give it is to say, based on all knowledge available to you, tell me the fully revised value of a given variable and in a given quarter. And we're going to focus on very important prominent variables, things like GDP, CPI inflation, industrial production, and the unemployment rate. For this paper, our focus is not on passing in additional data or context. So we're not going to be giving it historical values. We think it's interesting in its own right to see how much the models know in isolation. There's a lot of work potentially to be done on how they can access outside data sources. That's just not something we're tackling here. So we give it a bunch of these queries, then the LLM, if you've used these, it'll reply sometimes with a lot of text. And then I'll show that to you in a second, but there's a second stage that's just kind of technical where we take that wall of text it responds with and extract the estimate from it. So this is one response where we asked it, like, what was GDP in Q4 1945? It replies with a lot. And one thing that we see pretty clearly is that it doesn't just kind of know offhand. It's reasoning through what it knows about what was happening then and trying to come up with an estimate. So we think that's interesting in its own right, is that it doesn't just instantly say, yeah, I know exactly what GDP was then. I've memorized that. Here's what it is. It's really trying to come up with an estimate, just like you or I would. I should give you some more details. So we're really focused on Anthropic's Claude Sonnet 3.5. This is in part just because of the constraints in our technical setup. This is what we have access to easily. This model, it's somewhat outdated now, but it's still really good. Far better than like the GPT, than the original Chat GPT. Now it's 1 or 2 generations behind what you can get on your personal devices, but still very good. Another important point here is the randomness in responses. So if you know how these things work, you know that the responses are generally random. If you ask the same question twice, you can easily get different answers because they're set up to sample from the next word distribution at each step. You're not going to get the same string back if you ask the same query a few times. So the main thing we do to deal with this is to just repeat each query 10 times and average the results. So that gives us something that's more deterministic, still some randomness, but we feel that it's much more reproducible. It also gives us standard errors and confidence intervals, which I'll show you in a second. One interesting thing we found was that for the temperature parameter is usually talked about as something that makes it more creative or more random or more chaotic versus more deterministic. Say, like if you set your temperature close to 0, then things should be close to deterministic. We find that's really not the case at all. We actually find the temperature parameter makes very little difference for Sonnet 3.5, and setting the temperature equal to 0 doesn't make things deterministic at all. So our takeaway is that the modern models, the more advanced models, there's just a lot going on there. And the temperature parameter has some sway, has some influence, but don't assume that setting temperature equals to 0 is going to make things even close to deterministic. Okay, so let me show you some data. This is showing GDP. So the chart has a blue line, which is the fully revised actual value of GDP, so quarterly growth rate of GDP. The red line is Sonnet 3.5's estimate. That's the average of the 10 iterations for each quarter. And then there's a pink band around it, which is the confidence interval. You can see that pink band's very hard to see. The confidence interval is very, very narrow. So in practice, for these types of queries, there's not a ton of randomness in the actual answers or in the actual final answer. When we look at this, we see that it lines up fairly well. It definitely captures the business cycle. It knows when GDP was contracting and expanding, and in terms of like a recession versus a boom. But it really misses a lot of the high frequency volatility. You can just see that that blue line is swinging all over the place. And it kind of looks like the red line is averaging over those swings. We'll come back to that in a second. But the other thing that we take away from this is just that it looks like it does worse farther back in time. That seems reasonable given what we know about how the models are trained. There's a lot more training data from like the internet era, and not probably just not all that much available going farther back in time. Sometimes these statistics weren't even calculated in real time, depending on how far back you go. So let me show you another example. This is CPI inflation, so the 4-quarter CPI inflation rate. It's a much smoother series overall, but it also looks like the LLM is tracking it much better, especially say post 2000. It's picking up almost every little wiggle that you can see for CPI there. I think this is reasonably impressive. It does diverge as you go farther back in time. You can notice it's missing some of the troughs and the peaks as you get back pre-1980. Excuse me. But this is all, we think, consistent with the story about where the training data is and how much is available. Let me quickly talk about the recent history. So here we're really zooming in on the recent history, and the vertical line is the knowledge cutoff. So that's the end of the training data that went into Sonnet 3.5. One thing to notice is that it happily provides estimates for CPI after its knowledge cutoff. It just continues to make an estimate, and it has things trending down towards 2% inflation. What we thought was really interesting is that it seems to get worse, or rather the accuracy seems to get worse as you approach that knowledge cutoff. You can see in like 2001, it's the blue and the red lines are right on top of each other almost. As you get close to the knowledge cutoff, they do diverge. And we suspect that this is probably just, again, a function of the training data. Not everything that has been written about 2023 was written as of the knowledge cutoff. It's possible the companies are also buying tranches of data and they just don't get them at that most recent update of yearly data by the time training starts. So we think this is, we have some more in the paper about this, but it's potentially important to think about where their knowledge is most accurate. I probably don't have time for this, but this is documenting similar patterns in terms of bad estimates around the knowledge cutoff. Though we admit that this is a very small sample, there was a lot going on in 2023, so it's possible that this is just a function of the sample. So our kind of takeaways at this point are that Sonnet 3.5 does seem to know a lot about the historical time series of economic variables, misses a lot of the high frequency stuff, even for really widely reported series like GDP. It does worse if you go farther back in time, and it does worse very close to the knowledge cutoff, apparently. So now, yeah, let me quickly try to talk about look-ahead bias. So just to set the stage, we want to evaluate, like you could call them pseudo real-time forecasts. And this is where we ask the LLM to pretend to be a real-time forecaster, and this is what folks do in other papers. You give the LLM an instruction saying, you're a forecaster living on a given date. Give me your forecast for, say, 2025 Q2 GDP using only the information that would have been available to you as of that date. And then you see how good their forecasts are, compare them to professional forecasters, things like that. So the real question here is, can the LLM obey that real-time restriction? Do they have enough knowledge about what the real-time data looked like to ignore things that are in their training data, but would have only been known after the date that we give them? It's a really hard test because you can't just, like, the LLMs often do have good forecasts and can beat human forecasts. And you could take that as evidence that they are looking ahead, that they are peeking at the future data. But it could also be the case that that they're just better at processing data. We know these things have kind of read almost everything that's on the internet. So it also wouldn't necessarily be surprising if they just turned out to be better at processing dispersed information. So we can't just look at a good forecast and say, this has to be look ahead bias. We need to do something else. So our conjecture is that the LLM is smoothing together past and future data values. The LLM doesn't necessarily recall the exact value of GDP on a given date, but it knows when GDP was generally higher, generally lower. And so when it comes up with estimates, our suspicion is that it's just going to implicitly average together through like a rolling average. We're going to be focusing on recall errors, not forecasts, and we think this helps make our test a little stronger and more intuitive. So we won't ask it to forecast. We're going to ask the LLM to recall period T GDP using only data through period T. So that's our real-time restriction. We say don't use any information that came out after date T, just recall date T GDP using the history up to that date. We call that recall error term, and we measure the recall error there, and that's epsilon. Next, we compare that to the SPF forecast. So that survey of professional forecasters is like a good survey of professional forecasters that comes out every quarter. So we get the SPF forecast error for the next period's GDP. So this omega term is supposed to be the shock to GDP in the future that would have been very hard to forecast using period T data. Not necessarily impossible, but not something that the professional forecasters were able to do. And our position is that if epsilon t is correlated with this like very hard to forecast term, omega, it means that the LLM may have some like superhuman forecasting ability. They might be able to see a little bit of omega, but they're using it to make predictable recall errors for GDP. And that's where we think that shows that this is probably just look ahead bias instead. That it doesn't make sense to say that they're very, very good at forecasting, better than the SPF, but they're using that ability in a way to make really predictably bad recall errors. So I think I'm getting close on time, right? Yeah. This slide is mostly just saying the same thing again. So I can skip quickly to the table, and I apologize for being so rushed here. We test this in the data. We basically just regress epsilon on omega. If we find a statistical relationship there, we think that tells us that there is look ahead bias, and we can look at the root mean square errors to see how big that effect is. We do find that omega does significantly influence epsilon, or there's a significant association between the two. And it really does make a big difference with the root mean square errors, that this kind of peaking at the future that comes in through the omega term makes a significant difference with the recall errors. So that really tells us, to our mind, that it's just not plausible that the models are going to be both superhuman forecasters and making these really bad recall errors. We think it's much more plausible that they're just averaging through the future values of GDP, which they're not supposed to know about according to the restrictions. So yeah, just to wrap it up quickly, we think based on our analysis, these models do have a good understanding of at least the broad strokes of macro data, in some cases even much better than that. But they can't fully follow the directions that we sometimes give them, to ignore in-sample training data, to pretend to be a real-time forecaster. They just don't know exactly when certain things happened. So we have to look to truly out-of-sample data for validation. Okay, I'll leave it there. Thank you all.
All right, thank you, Leland. Let's go ahead and move on to Adrian, who's next.
Yep, thank you very much. I'm going to share my screen. I think it's okay. You can see it.
Yes, we can see your slide.
Okay, so thank you very much. So I'm Adrián Pérez. I'm going to present this work I developed with my colleagues Carlos Saez, Sebastián Gallego, and Andrés Jurado. We work on the methodology and sampling design department in statistics Spain. Okay, I'm going to present this work titled Synthetic LLM Generated Text to Train Small Models for Automatic Coding. Maybe a bit cryptic, but now you will understand well what is this all about. So let me introduce briefly what this challenge is about that we faced. I guess most of you know these statistical classifications. We have this family of statistical classifications. We have statistical classifications for economic activities, for products, for goods, etc. And we have this hierarchy, let's say. We have the world level classifications, in our case, the EU level and the national level. So in this specific talk, we're addressing the economic activities classifications. So most of you probably know about the ISIC classification. Here in Spain, we have, it's called FENAI, our national version, but it shares most of the characteristics of ISIC. So these last years, these classifications, these economic activity classifications, have undergone a revision. So, well, they were reviewed in parallel. The ISIC, the NACE, that is the EU one, and the FENAI, that is the Spanish one. And now we have these new versions, and as you may guess, there is a huge challenge to code and recode economic activities with these new versions of the that, by the way, are quite different from the previous ones. So, well, the challenge. We needed to implement a tool for both coding assistance and automatic codification of pre-text economic activity descriptions. So we wanted to make it available to all kinds of users with diverse knowledge levels and needs. This means that maybe some users of the tool will provide very technical and detailed descriptions, while others may provide fuzzy ones or even very short, even just single words. And well, we have this nice to have, that the solution should be easily replicable to other statistical classifications or versions of the same classification. Yeah, to avoid doing replicating all the work each time that we need one of these tools. So, well, we arrived to this point where we need to choose an approach, right? So the first thing that comes to mind is, okay, let's build a machine learning model. So of course, based on NLP techniques, maybe some classic ones such as bag of words or LSTMs, fast text, that is a very shallow neural network, or well, more state-of-the-art ones such as BERT-like models. Of course, we need to gather a data set for training, validating, and testing. And here, well, we started addressing this, and we found some limitations. First, the data gaps. Gathering enough data is unfeasible, especially for some classes. Have in mind that this classification specifically has almost 700 classes. And what's more, each class contains, let's say, we could think as them as subclasses, some contents that are not, let's say, homogeneous. So in practice, we have thousands and thousands of economic activities. And even if we have enough samples at first sight for a class, for instance, let's say we have 100 samples for a class, some of the contents that are included in that class can be almost empty or completely missing. Apart from that, the data that we gathered showed a variety of quality issues. So many different issues, ambiguous descriptions, incorrectly labeled text. We found quite a high percentage of incorrectly labeled texts. And then, well, many inadequate texts, such as company names, text in other languages, or too different from the expected inputs. And apart from all that, most of this solution wouldn't be replicable. If we want to build another model, let's say for the product statistical classification, we will need to build it from scratch. So, okay, we have this alternative. Okay, just ask ChatGPT, right? Or any other LLM. So we'll know that large language models show outstanding capabilities on a variety of problems. In our case, we couldn't afford to deploy them on premise, so we need to access them via API. And well, first we tried zero-shot or few-shot approaches. They produce poor performance. Okay, so what about RAG, Retrieved Augmented Generation? Well, some of the previous speakers also talked about this technique. It's a powerful technique. However, implementation is not trivial, not, let's say, plug and play. And apart from that, well, you still have some hallucination risk. You depend, as we need to use, as we have to use these LLMs via API, so we would depend on a third-party service in production. Responses vary given the same prompt, which is of course not ideal, and cost is hard to predict and may escalate. If we had millions of requests, that is quite realistic, it could escalate too much. So okay, we have this third approach, which has been named ZeroGen, efficient zero-shot learning via dataset generation. I suggest that you read the original paper. It was published in 2022. And well, basically it takes the advantages that we all know of LLMs without most of the downside that we have just explained. So how does it work? Well, so it's a very simple idea, say simple but smart. You need let's say three inputs. Prompt that, well, consists on a prompt template that you fill with each category, title, and if you have, in this case, we have, apart from the title, explanatory notes. So all the information that you can give to the LLM to generate synthetic data. Then you need a pre-trained tiny task model, such as a fast text or parrot model, and a test set, in our case, very small test set to just check that that the whole solution is working. So once you have these three elements, you inject the prompt on an LLM, and you obtain synthetic text. You just ask the LLM, very simple idea. You ask the LLM, okay, make up descriptions of companies that do this economic activity. So you get, we generate 20 per request. So you get 20 per request, you get 20 pairs of text and code. Then you aggregate all these pairs into a data set, and you just train a model on that data. Very simple, very easy. And well, of course, you get metrics on your test set, and if it is satisfactory, you can deploy it into production. Take into account that the labeling here is almost perfect, okay? Unless the LLM generates some wrong description, but that's very unusual because you're giving very specific descriptions and very specific notes. And well, we can combine this, of course, with real data. And this is our actual implementation, our actual strategy. And it's basically doing all that I have just explained, but also using real data and combining the real data with the generated data. Okay, so if you review the literature, we can see that ZeroGen is presented as an alternative when real data is very scarce or unfeasible to get. But it is shown as always worse than training on a reasonably sized real data. So it's like a worst case scenario, let's say, an alternative for worst case scenario. However, in our case, well, you can check the metrics here. The accuracy, for instance, it competes with the classic ML approach. Okay, so using only synthetic data produces this equal or even slightly better results than classic machine learning. And of course, the best approach is combining the two of them. Okay. So well, we developed, after all these experiments, we developed and trained the model, developed a tool that is called Code IA, Code AI in Spanish, let's say, and it's already in production. We have had 125K requests during the first 100 days, so quite successful. And we have had satisfactory performance in production. We labeled a small sample of real production requests, and we got these metrics. This is a precision versus recall curve, taking into account the logarithmic like x-axis, but well, without entering into much detail because we don't have a lot of time. You can go to the, let's say, for the automatic coding scenario use case. You could go, for example, here with approximately 50% recall, so coding half of the descriptions, we get a 90% precision. And if you go to the other side, to the assistance tool, let's say, with 100% recall, we get to also 90% precision, but of course, not with one output, one possibility, but showing in average about three outputs. Okay. So conclusions. Zero-gen approach shows outstanding performance. We were very impressed with this, at least for coding statistical classifications. So similar performance to classic ML approaches, which are much more demanding on data collection, cleansing, etc. And way better if combined with them. Regarding the machine learning models, we used for hardware, because of hardware constraints, we finally used fast text, which is very light. But if you can afford it, it's better. BERT-like model produce better results. So thank you very much. Here you can find my email address if you want to contact me later. And thank you very much.
All right, thank you. I'll just remind everyone the Q&A is still open for you to ask questions. We'll try to answer them either in the middle by the author, or we can save them to the end. But let's move on to our third speaker, Atul.
Are you able to see my screen?
Yes, we can. Thank you.
Okay, perfect. Oh, I'm still seeing the previous screen. That's weird. Give me 1 second. Let me figure zoom out real quick here. Okay, well, as long as you can see my screen, I'll do that. All right. So thank you everyone for being here. Today we're presenting one of our pilot studies that we've kind of started to see how we can use large language models a little bit more easily or better for helping people better understand data sets that are produced by the Census Bureau. The outline of the talk is fairly simple. We'll start with a quick motivation behind the work and then lay out the problem statement. And then we'll kind of give a brief overview of the knowledge graphs and causal learning. Then we'll do a deep dive into the proof of concept example where I'll go over the data set we've used, the use of large language models for generating the knowledge graphs, and then also using traditional statistical techniques like structural equation modeling and structural causal modeling to validate those graphs, and then input that data back into the large language model to then produce a large language model or causally enhanced knowledge graph. Then we'll quickly wrap up with summary and what's possible with these techniques. So the motivation, as we mentioned, for this work is kind of for folks to be a little bit more curious about the data sets they're using, especially with Census Bureau's data sets. You know, we produce a large and vast amount of data, and most of these data sets are used on a regular basis, sometimes for policy making and decision making. So we want folks to be able to understand the actual details behind the data sets, like actual causal reasoning, the causal effects between the variables and everything. And the secondary motivation for us is to kind of highlight the utility of AI tools like large language models to make that decision-making process a little bit more easier and more efficient. While large language models do have their own issues and challenges, They're kind of at their core built to make life easier for folks. And that's kind of what we're trying to highlight here, saying, even if you're not completely tech savvy, even if you don't know how to code in Python, use large language models, because they might not be always 100% right, but they'll at least give you a little bit of push on the right direction that you might not have originally. So especially, for those folks, these large language models are kind of built as a bridge for that technical gap. So with that, the problem statement for the study that we're trying to prove is that despite the richness and scale of large government data sets, such as the American Community Survey or the EIS, extracting reliable causal information from these high-dimensional observational data sets remain a persistent challenge. Traditional statistical methods for causal inference often require extensive manual preprocessing, domain expertise, and structured assumptions, which sometimes limit their scalability and adaptability to new variables or evolving research questions. To kind of address that challenge, we have utilized a large language model assisted framework with causal discovery techniques to automatically generate interpretable and validated causal graphs, enabling data-driven policy analysis and decision support. Next, there we go. All right. So knowledge graphs, everybody has used some before, and I've seen one before. Knowledge graphs are a visual representation of information in data sets where nodes represent the different variables and edges represent the relationships between those variables. These graphs are semantic and provide a wealth of information about the data that they are generating the knowledge graph from without the need for folks to run additional analyses. So these kind of provide you a high-level overview of what the data is telling you without actually having to run full complete scripts for you to get the same data or the same analysis insights at least. They also provide a wider degree of flexibility for their use. They can be used, by data scientists, but also by decision makers who don't necessarily want to do a lot of the computing and the analysis themselves. Next one. Okay, so causal learning. Causal learning itself is the process of identifying and estimating the cause and effect relationships between the variables in observational data, while traditional machine learning and statistical learning are based on correlation. Causal learning goes a little bit further and actually identifies the cause and effect relationships. And that's kind of what we're trying to highlight the use of large language models for, to identify those cause and effect relationships. So our framework is then kind of very simple or straightforward at least. We choose a ACS data set and then we choose a smaller subset of it just because this is a pilot study. And then we apply that data set we upload that data set within the large language model and then ask it to generate some causal hypotheses and generate a causal graph. And then using that causal or that knowledge graph, we then apply the same data set to statistical equation modeling using a Python library called SimaPy. And then we use DoI, which is a causal library in Python as well, to actually estimate the causal estimates. And then we then input those results back into the large language model to then ask the large language model to incorporate those causal estimates directly into the knowledge graph, and then produce a causally enhanced knowledge graph at the end. So kind of our proof of concept study really kind of utilizes a very small subset of ACS data. I just want to mention that because this is a very, very pilot study, so we don't have hundreds of thousands of variables. We're just using a very small data set. As I mentioned before, the methods are fairly simple. You take a small subset of ACS data set, input that into a large language model. We prompt it to generate a causal hypothesis based on the data set, and then prompt it to generate a knowledge graph, and then prompt it to also generate some kind of correlation-based DAG, which we can use later. And then we use statistical validation using SimaPy for structural equation modeling and DoI for structural causal modeling. Then we feed those results back into the large language model and then ask it to generate a causally enhanced knowledge graph. So the data set we used for this pilot is a ACS 2015 to 2019 set of 50,000 samples. It includes variables such as age, sex, race, marital status, education, and income. We used this specific features because we wanted to kind of copy the census or the UCI repository's census income data set, which has similar variables and features. So we kind of wanted to see how large language models are able to provide analysis on real world data sets rather than 25-year-old data sets. So we took that data set of 50,000 samples and then input it directly into ChatGPT. Oh, sorry. For our purpose, we use ChatGPT 4 Omega, just mainly because it's one of the more popular ones. We haven't done a comparison with what this would look like in Gemini or Claude. We will do that later down the road, but at least for this study, we only use ChatGPT for now. No specific reason, just because it was available. So we took the data set and then uploaded directly into the large language model and then asked it to infer likely causal relations based on its own domain knowledge that it's trained on, and it's able to actually produce these causal relations that's based on its own theory. So for age to education, age to marital status, age to or education to occupation, sex to race, race to wage, and marital status to wage, all of these different causal relationships it's able to identify, not on any specific causal algorithm, but just based on wide domain knowledge that it was trained on. We then asked it to then generate a knowledge graph based on those variables and the data set, and it's able to give us this. So here it says sex correlates with education or income, whereas education affects income, and then race correlates with income. Here we want to kind of really highlight the different words it's using. We asked it, what's the difference between correlation, influence, and effect? Because in day-to-day life, these are kind of similar. So we said, can you let us know what the actual meaning is between this? And it said correlation implies a statistical association, not necessarily a direct causal link. It's used for weaker symmetrical relationships, whereas influence suggests a directional effect, possibly a causal or mediated through a pathway, used for moderate predictors such as age through education. And then finally, effects includes a stronger, more confident causal interpretation of influence within the data set. So there's 3 different sets of relationships it's able to identify using its general domain knowledge. So then we took that kind of knowledge graph and then asked it to build a correlation graph, if it can, based on its own environment. And it's actually able to generate some of these correlation data using its own environment and running a Python script directly within the ChatGPT environment. And it's able to then give us a more or less direct data correlate graph with actual correlation numbers within it. So now we have these knowledge graph and more or less a correlation causal graph. We wanted to kind of see how good these were and validate these using traditional statistical and causal methods. And as I mentioned before, to do that, we kind of used a traditional greedy equivalent search to generate an actual causal graph. And then we did structural equation modeling and structural causal modeling, and then feed that data back into the large language model to then generate the final causal graph. So the first thing we did was use the GS equation to generate a causal graph. Here, the difference between the causal graph or correlation graph that the large language model created was that instead of 3 variables having an effect on income, the causal graph is able to identify an extra variable, which was the marital status. The original large language model only identified sex, race, and education, whereas here, marital status is also highlighted as having a direct impact on the income label. And then we ran statistical equation modeling via the SemoPy library and Python. And then we set our equation to be income is independent, or income is dependent on education, sex, race, age, and marital status. And when we ran this, we got an R-squared value of 0.644, which is not the best, but not the worst either. So we're like, okay, it's fair enough. And then we calculated the predictors to show which variables actually made a positive impact or a negative impact. And here it shows that education has the highest and positive impact, more education, more income, which made sense, but it also highlighted sex and race as having a negative impact. So, being a female or coded as 1 would make you have a lower income than male, which is coded as 0. And also for race as well, being coded as anything other than a white male, the farther you go, the lower income you had based on the structural equation modeling. We then kind of ran similar validation using actual causal modeling using DOI with a linear regression model within DOI to calculate the actual causal estimates for each of these different variables on income. And kind of similar to the structural equation modeling numbers, we once again got education as the highest predictor, but sex and race also once again gave us a negative kind of relationship between that and income, showing that, females once again are earning less, and then race also has an effect directly on the income of a person. So with that, we kind of fed the SEM model data set directly into the large language model and asked the model to then generate a causally validated graph based on the table that we provided. And it's able to provide something like this, which kind of gives us a actual causal estimate along the node with the definitions of whether it's associated with, whether it's negatively affected, whether it's correlated, whether it's influences. So going from a simple, or I guess not as causally relevant knowledge graph using simple domain knowledge from large language models, by applying structural causal modeling as SEM, we're able to then generate a much more, I guess, insight providing knowledge graph that actually gives you a better analysis of what the actual causal factors are within the data set. We do want to highlight that while we had to run the SEM and SEM directly on our own environment in Colab, if you're able to have a local environment running of a large language model, like of Llama, you should be able to run these scripts directly within that, as long as you have the provided libraries installed within that environment. One of the drawbacks of these open source cloud-based models are that their environment doesn't include all the libraries. So if you're able to have your own local one, this kind of provides you an end-to-end library of using the whole, generating all the results within the same large language model. So in summary, we introduced a framework for combining large language models with statistical techniques to generate interval causal graphs. These large language models can generate causal hypotheses using metadata, variable descriptions, and domain context, whereas statistical models like SEM or SEMs can then validate these graphs using empirical data. This approach supports a more robust and explainable and policy-relevant inferences from complex survey data sets. As I mentioned before, a large or local large language model with the required packages would be able to run the SEM scripts within its own environment and produce these statistical validations without the need for external programming via either Jupyter or Colab that most of the people use. And with that, I will take any questions. I know I speak really fast when I go, so apologies if I talk too fast over something.
Yeah, so thank you. Definitely, please put them in the Q&A feature. At this time, though, let's go ahead and welcome our final speaker for the session, Arina.
Can you see my screen?
We can, and we can hear you.
Can you hear me?
Yes.
Okay, so let's get started. Good afternoon, everyone. Thank you for joining us today. And my name is Arina Bilaeva, and I'm with US Census Bureau. And today I'll be presenting integration of statistical survey metadata with large language models using knowledge graph. So this work was, we worked together with Chris Karin and Rich Ivan, Chris and Census Bureau. I would like to thank you them for invaluable contribution. So this presentation doesn't present like a views of the Census Bureau, but a presenter. So let's get started. To give you a roadmap of today's presentation, I will be covering a few areas. First of all, I provide a background on knowledge graphs and how they integrated with statistical survey metadata, as well as I show a couple use cases where they we demonstrate how this technique they complement each other. First of all, let's talk about what is the statistical survey metadata and why they important. The statistical survey metadata is a foundational for how we interpret and understand the data. They consist of variables. In these variables, they don't live in isolation. It is very important when and how data was collected, what population was used, and how this measurement is defined. When we consider integrations of the LLMs in the workflow, we must ensure that these models they have access to statistical metadata, so they don't misinterpret or hallucinate about how what data is they actually represent. And in order to do that, we have to unlock the semantic layer. So basically, the sensor bureau produced data, they consist of two parts. It is metadata about data and the data by itself. And in order to make sense of this data, we have to use advanced processing techniques such as natural language recognition and large language models to fully understand how these LLMs they can interact with statistical data. So let's take a look why LLMs they provide so promising interface for metadata and data exploration. So first and foremost, their strength is, belongs to in understanding natural language. It makes them very intuitive for users, researchers, and other policymakers that can explain and ask questions in a natural language. However, there is a catch. LLMs they can misinterpret facts if they are not grounded in structured and domain-specific information, and that's where integration with knowledge graphs has become basically essential. If you take a look at the pros and cons, these two different complementary techniques, so we can see that LLMs, they excel at language understanding, they provide adaptability and generalization, but and they also can interpret vague statements in the natural language and convert them to the structural queries. However, LLMs, they lack grounding information in the actual facts and can hallucinate. On the other hand, if you take a look at the knowledge graphs, they provide structured and symbolic knowledge where we have clearly defined relationship between entities. They provide interpretable and domain-related facts that help with generalize across many data points. So if we can see here, when we combine two techniques together, LLMs with survey metadata, knowledge graph, we can achieve a balanced system. So knowledge graph is grounds the LLM, and LLMs that don't work, making this knowledge more accessible and intuitive to query. Let's take a look how integration LLM with knowledge graph can actually take place. On one side, we have LLM, a model trained to understand and generate a human-like text. On the other hand, we have a structured knowledge graph that contains the metadata and relationship and like other connections. So by fusing these two techniques together, we enable a semantic metadata reasoning, the process where LLM can interpret a user query in the context and map to relevant information in the knowledge graph. Here we break down this integration of LLMs and knowledge graph in more detail. Here we have on the knowledge graph side we have functions such as structured knowledge, domain knowledge, and interpretability. On the other hand, LLM have language understanding, generalizability. What it allows us to do, first of all, integration LLM and knowledge graph allow you representation learning by learning entities, relation, and extracting concepts. On the other hand, when we put this framework together, LLM allows knowledge graph allows to perform LLM grounding in the fact using such techniques such as retrieval augmenting generation. What it gives to us, we can create very exciting application that, for example, semantic information retrieval, topics, and concept discovery, as well as many other applications such as question answering. Let's take a look how we can construct a metadata knowledge graph. First of all, we start with enterprise relational metadata model. In many organizations, including Census Bureau, information about data that's stored in the enterprise repository. So in this, in our goal is to translate this entity model in a structured knowledge graph. So as we can see here, the central concept is a statistical variables, and usually statistical variable is related to it was produced, initiated in like some program, subprogram, and is associated with some topic. Normally, the variable also placed in the variable group, also called table, and it also sometimes depends on the survey. It's associated with a code set and associated like code set type. To formally introduce how enterprise repository can be transformed to the knowledge graph, basically we derive a map that transforms a relational entity model into knowledge graph using this function. So this outputs a collection of triples which provide a subject relation object that understandable by both like humans and machines. So this results in a creation of survey metadata knowledge graphs that support semantic enrichment, LLM grounding, as well as a data asset discovery. Given previous background information, how we construct a knowledge graph, let me actually explain how we come up with this model. So this slide illustrates the schema of the survey metadata knowledge graph in more details. So here we can see that each variable is represented as a node connected to topic, code sets, subprograms, and programs. So we define a specific relationship like uses, part of, defendant, and child of to capture structure and semantics of this metadata. For example, a variable might be part of a variable group, belong to topic, be defined in a specific survey, a program, and use a particular code set. So these structural relationships, they enable advanced semantic queries, not like keyword searches, and help LLM perform grounded reasoning over this metadata. This model also aligns with standards like generic statistical information model, making it like more extensible and available for understanding and integrating with other statistical frameworks. Let me go a specific example how instance of the graph was constructed for a specific a variable using a data set by business dynamic statistics. As you can see here, we have a variable name that's called establishment that provides information about number of employment establishment for industry, machinery, and manufacturing. So here we map a variable name and variable definition, as well which group it belongs, which code set it belongs, North American industry classification, and which code set item is defined, as well as which survey, in which survey it was produced, in economic surveys, by program, by account program. So far, we have talked about symbolic structure of our knowledge graph, but what happens when you want to do like mathematical operations on this knowledge graph to enable other applications? In order to do that, we have to transform human understandable representation in the graph in the knowledge graphs embedding. What it gives to us is provide a symbolic structure, provide preserve a relationship, as well as unroll semantic paths. And from the user perspective, application perspective, it allows to perform like many operations and enable many fascinating applications like search on graphs, topics, variable discovery, as well as question answering using LLM reasoning with retrieval augmented generation technique. Let's take a look how we create a knowledge graph embedding. To use it, we can apply a technique called RDF graph embedding, and it is technique that allows to walk over RDF style graphs and generate sequences or like paths that turns properties and relationship graphs in the mathematical vector. In this example, we can see that variable establishment was defined in economic survey and uses classification code 333 and which part of the North American classification system. So this allows us to define a generate a vector embedding. So these embeddings can be used to measure similarity between nodes and as well as support like different semantic ranking in the search, or they can be fit in the topic modeling algorithm. And this type of embedding is very well retained structure and semantics of the metadata. How we can use overall set of these techniques, graph, knowledge embeddings, and LLMs together. The previous background on the knowledge graphs and their translation in the mathematical representation that allows to use apply different fascinating applications. And in this talk, I'll describe two applications that we explored and validated. The first task is LLM augmented search using survey knowledge graph, and it was evaluated. Performance was evaluated using retrieval quality metrics and candidate rankings. In other topic, in other application we evaluated, it was data-driven topic discovery using LLM techniques, which was evaluated using semantic quality metrics. And why this task is very important? As we know, US Census Bureau have a number of statistical data products, and our one of the many missions it is provide user with disseminated data, and as well as provide the ability to discover this data and use for a purpose for different audiences. One of the second application, topic discovery, is actually very important topics.
Sorry to interrupt. You are at 16 minutes. If we could try to wrap up, I'd like to save some time for questions.
Okay. I just demonstrate my results on the next couple slides. Let me move on the results. So let me explain results of the task 1, which is LLM augmented and semantic search. We evaluated and compared knowledge graph versus plain LLM and RAG techniques. And we use the metrics such as semantic ranking, which includes precision at k, recall at k, and normalized discounted cumulative gain. So using, as we can see here, LLM and knowledge graph, they showed higher performance across all metrics, which indicates more relevant and better performance of the knowledge graph. The second technique we evaluated, it was evaluation of the performance of data-driven topic discovery using LLM techniques. Here we compare these techniques with plain techniques such as bidirectional encoding transformer topic technique. And we use 2 metrics that topic coherence and topic diversity. And the result demonstrated that LLM on graph that allows to outperform other per topic and provides more coherent and diverse topic that contributes to understanding sense of data more fully. And it is crucial for maintaining metadata and allowing users to navigate across a vast amount of sense of data. This concludes my presentation. I put a number of references for your use in your research if you desire. And thank you so much. And please feel free to reach out if you have any questions. I'm happy to answer. Thank you so much.
Yeah, thank you to all our speakers today. We do have some time for some questions. This question coming from Alice was actually, I think, originally asked for Leland, but I'm curious to hear what some of our other speakers might think about this. It sounds like more people are using LLMs for decision making. Is there any concern that using LLMs just broadly to help make decisions for us will lead to a self-fulfilling prophecy?
I mean, I'd just add that I think there's definitely risk, and I think the AI labs know this. There's risk when you're training on the data that the model generates. I think, at least for forecasting, we're not quite there yet. I think folks who use this use it in a very indirect way, and there's a lot of human judgment. So hopefully there's still a lot of signal. But I'm sure at some point we'll maybe hear about weird things happening where an LLM is consuming its own output, or another model is consuming its own output.
And I'm curious because I think a couple of our speakers are using knowledge graphs, for instance, or RAG to sort of provide additional information that maybe wasn't in the original training data, and then asking the LLM to do initial analysis on that new data. Does that add an additional concern? Maybe Atul, you could weigh in here.
I think from our perspective, we kind of wanted to use the traditional techniques to validate what the large language model was producing. We wanted to make sure, like, yes, trust the large language model, but with a grain of salt. And that grain of salt being, your own expertise on validating these answers that the large language model is giving you, because they're known to give you harmful results eventually, but you don't want to just take it blindly.
And Atul, you had another question about from Elizabeth. asking whether you did this in the ChatGPT chat or all in the same chat. Some more specifics about.
Yeah, we used the ChatGPT for Omega directly. Every time we had to kind of stop for the day and then come back, it resets the environment. So you have to re-upload the data and some of the graphs that it had produced, and then ask it the question over again, be like, hey, here's the data set, here's the graph you produced. Can you now give me additional analysis?
Thank you. That is all the questions that we currently have. Feel free to keep asking more questions. In the meantime, I've got one, I think, for Adrian. I noticed that throughout your talk, you really emphasized techniques that would work well in sort of what I would consider a lower compute environment. Do you have more advice for us who are trying to explore LLMs in that kind of situation?
Well, I think the easiest thing to, yeah, in our case, the easiest thing to do was this, because accessing LLMs via API, be it OpenAI LLMs or even Grok LLMs that is Grok with not with K, but with Q, not the Elon Musk one, the other one. They are free, so accessing them is very cheap on a computational point of view, and yeah, training fast text or even bird-like models on a regular laptop is completely feasible. So yeah, this is the approach that we took. I know that there are ongoing efforts on making LLMs, proper LLMs, let's say using proper LLMs on premise easier from a computational point of view. And there is this, this distilled LLMs or this LORA, like LoRa techniques for training just a subset of the weights. But I'm not very familiar with these techniques, but I've heard about them. So if you have, let's say, mid hardware constraints, they can be an alternative, I guess.
Yeah, thank you. All right, well, I don't see any additional questions in the chat. Do any of our panelists have questions for each other, maybe? We have about 3 minutes left. Okay. Okay, well, I'll go ahead and hand things a lightning round.